homeworks are due when they say they're due on a day. It's due by the end of the day. So 11:59 p.m. Friday night, that's the actual deadline. These are all submitted through Gradescope. Let me know if you have any issues with Gradescope or questions about it, but probably you used it, I don't know at this point. But anyway, if you haven't, and you have some confusion, you can let me know. But anyway, you just make a PDF of your homework and submit it through there. And just make sure you do the step where it'll ask you to match the pages of your PDF to the problems from the assigned papers. So on our end, it'll show the right page when we're trying to grade the problem. So don't skip that step. Okay. But anyway, the system is set up so that after 11:59, you can't submit. Like it'll lock you out. That is actually like a hard deadline in the system. So so please make sure you get it in on time. Okay. You guys have any questions or concerns? Anything? So if not, we can return to our discussion of greatest common divisors for integers. So we defined what these were last time. We looked at a few examples. We also gave an important definition last time about integers being relatively prime to each other, and that means that they have a GCD of 1, greatest common divisor of 1. So there is first just one result about GCDs we want to go through because it's occasionally a useful device. So this is the reference in the book. It's following proposition. So if you have two integers, let's say a and b, if a and b are integers with a certain GCD, let's say, we don't know what it is, it could be anything, but we're going to call it d right here in this statement. So the statement here is that there's a way to produce a pair of relatively prime integers out of a and b by just dividing out by what they have in common. So the statement here is that if you take these two integers and divide them each by their greatest common divisor, then what you will get will be a pair of integers that are relatively prime. Okay, so again, in this, in a number theory course, we're always working with integers. You should always be like a little bit careful when you start writing fractions now, because fractions of integers might not be integers. But in this case, those are definitely integers, right? Because d is a divisor of both a and b. So if you divide it into a or b, you get an integer. So that makes sense. Okay, but anyway, that's the statement. So this, as a device, is sometimes useful. Like there might be cases down the line where we want to prove something, and it's like easy to prove it in a relatively prime case. Like say the numbers are relatively prime, and you can give a proof there. And then this is sometimes used as like a way to reduce to the relatively prime case somehow by talking about those things instead, which are relatively prime. Okay. Now, anyway, we'll prove this. So let's give a proof. So, okay. So, what's the goal here, right? So the GCD, we want to prove it's 1. Just something to remind you about. Maybe just as a little note we have here. I'll just leave this in parentheses just to remind you. Any GCD at all is going to be at least 1. Okay, so that's true about any GCD at all. So like it'll be greater than or equal to 1. So what we'll show here, in the context of this proof, is that we'll prove that the GCD of this pair of quotients here, what we'll actually show is that it's less than or equal to 1. Okay, so that's will do the job for us. Right, so it has to be greater than or equal to 1, like any GCD. But we'll show this. Okay, and then if we show that, then we're done. Okay, so then how do you show that? How do you show that the greatest common divisor of these two things is less than or equal to 1? What we'll do is we'll show that any common divisor do is we'll show that any common divisor of these two numbers of what's it, a over d and b over d. We'll show any such thing as less than or equal to 1. So that's the plan. Okay, so that's the strategy. And so then we'll start with any such thing. So let's let C be such a thing. So let's suppose then we've got a common divisor. So suppose C divides A over D and C divides B over D. And so that is saying C is a common divisor of those two integers. Okay, and so let's run with that. Right, so what does that tell us? It tells us just the definition of divisibility tells us this then. So A over D has to be C times an integer. Right? That's what this means. So it's C times something else. We just need a new letter. Let's go with E. Right? So it's going to be C times an integer E. And over here, B over D likewise has to be C times some integer, which is probably a different integer. We'll give it a different name, F. Okay, so that's what we get out of the assumption, and then we have to do something, right? So what do we do? So, well, we know something about, I mean, at least we know what D is. D relates to A and B. It's the GCD of A and B. So anyway, a natural thing to do with these things if you want to try to manipulate some stuff is multiply out by D. And like solve for A, solve for B. Right, so what happens here, if you do that, is from this equation you could write it as A is C times D times E. Okay, and likewise B is C times D times F. Okay, now here is the thing then. So I want to say something about C, and the thing to notice here, I guess, is this. Right, in both equations, that's a common factor. You've got. So it's some kind of common divisor of A and B. Right? So what this shows, right, so far, is that C times D, whatever that may be, this is a common divisor of A and B. Right? But on the other hand, what we do know is that D is the GCD. D is the greatest common divisor. Of A and B. So there's something I was a little sloppy about I should fix over here. So let me just try to amend things a little bit. So what I meant to do along the way is assume C is positive, which is probably what you're thinking anyway. But let's just assume. Oh, maybe I don't need to do that. No, I don't need to do that. Okay, forget it. Okay, anyway, back in over here. The point is, we have a common divisor of A and B, but D is the greatest common divisor of A and B, which means whatever this thing is, it has to be less than or equal to D. Okay, so what happens here is D is the greatest, emphasis on greatest, of A and B. So what that means is this other common divisor we stumbled across cannot be larger than D. Okay, and there you go. So that implies C is less than or equal to 1. You could divide both sides by D. Okay, so divide. That gives us what we want, right? C is less than or equal to 1. Okay, we could divide both sides by D, and D is not 0, so dividing is okay. D is not negative, so it doesn't flip the inequality or anything. Greatest common divisors are always positive. So that's all okay. And that gives us what we wanted, right? So C, what was C in the story? C was an arbitrary common divisor of these two things. We just showed it's less than or equal to 1. Okay, so that's what this was. This has been established then. So any common divisor of these two numbers is no more than 1. Okay, so basically end of proof. As desired. questions on any steps or anything? Okay. All right, so that is a fact about GCDs. I mean, the next order of business for us is to talk about actually computing these, and it's a more practical thing, like how do you actually compute them, especially like on an algorithmic level. Like what if you had humongous integers, a pair of humongous integers, and you wanted to know their GCD, which is actually something that has applications in things like cryptography and so on. So anyway, suppose we had such a thing. How would we compute GCDs? So that's next order of business. So this is actually a really important section for us. There's something called the Euclidean algorithm. Which is something we'll end up needing a lot. But the motivating question is how to compute GCDs. Okay, so I mean, this is not meant to be a super challenging question when you just have like a couple two-digit numbers in front of you. Okay, like I figure it out, but it's more of like, what if you have two 100-digit numbers in front of you and you want their GCD? Okay, so that's a whole different story. Now, okay, so stepping back from that extreme-sounding thing, like what if you just have 2 or 3-digit numbers? Here's one approach you can make, which is like slightly cheating based on where we are in the course, but it turns out to not be a good approach anyway. But this might be something perhaps you would have learned about a long time ago. But one approach could be to factor the numbers. Okay, so into primes, say. So, for example, here's something you could do, which would be, I guess, valid. But if, say, you wanted to compute the GCD of something like 220 and 315. Okay, so something you can do is this. So let's say you took 220 and you tried to start factoring it. Right? So you start factoring it, let's say, I don't know, it's 22 times 10, right? So let's start there. It's 22 times 10. And then 22 is 2 times 11, and 10 is 2 times 5. Right? So you have 2 times 11 times 2 times 5. And that looks like 2 squared times 5 times 11. And that's a factorization into primes. And then you could take 315, which maybe it's not totally obvious how it factors, but it's definitely got a factor of 5 in it, right? Because it's a multiple of 5. So what is it? It's 5 times, what is it? 63. 63? Sounds good. Yeah, 63. Yeah, so then I mean 63 you could factor too, right? That's, or that 9 times 7, right? So this is, okay, 9 you can also factor, that's 3 times 3. So I guess we have something like 3 squared times 5 times 7. Okay, now these are prime factorizations, and I mean from prime factorizations you can in fact deduce what GCDs are, and this is I guess something that formally we haven't proved or something. But this might be something you learned a long time ago, greatest common factors or something, which is the same as what we're talking about. And when you look at the primes they have in common, the only one is really 5, and you could deduce from that, since 5 is the only factor they have, the only prime that's kind of shared. The GCD of 220 and 315, in fact, is 5. Now, again, this is a valid approach, but it's something we haven't quite established. And what I wanted to tell you, pause right now to tell you, is that to justify this, facts about prime factorizations of integers, and the fact that you can do it, and the fact that they are unique. And basically, this kind of an argument relies on some things we haven't really done in the class yet. So one of the things that we're going to do in this class, in the coming week or so, is we are going to prove that integers have prime factorizations and they are unique. It's kind of a big theorem in number theory. It's called the fundamental theorem of arithmetic. And that's something we're actually going to carefully prove, and it's not as easy as you might think. It takes a little bit of effort. Okay, so what I did want to say, though, is actually we don't really want to be relying on prime factorizations right now, or arguments that revolve around prime factorizations. And in particular, what I wanted to also say to you is on your homework right now, don't base any arguments around prime factorizations. That's like facts we haven't established yet. Okay? So, all right, fine. Now, anyway, this is, once it's justified, it's a valid approach, but it's not a good approach, actually, to finding prime factorizations. So there are issues with this right here, as it is. Okay, and so let's say this doesn't work. Let's say work well or at all, really, for large integers. And the thing is, because at some point when your integers get big enough, factoring is not really a feasible problem to solve. Okay, so factoring large integers, let's say on the scale of something like hundreds of digits, is actually not computationally feasible. Okay, so this is just something that's good to be aware of as a general fact about integers. It's something that a lot of cryptography relies upon, and later in this course we'll spend a little bit of time with cryptography. But the thing is, just something, when we say it's not computationally feasible, it means like even with the aid of a computer, you can't really accomplish it in your lifetime. Okay, so what this means, like if I, just imagine this, say I, behind closed doors, found two 300-digit prime numbers and I multiplied them together and I made a 600-digit number, which is not prime, it's composite, it has two prime factors. And then I handed you this 600-digit number and said factor it for me. The point is there's no good computational way to actually do that, like even algorithmically on a computer, okay? Okay, some cryptography relies on that fact. So anyway, that's means that if you wanted such a GCD with numbers on that scale, you can't do this. This would never work, really. And so anyway, there is actually an approach, though, to finding GCDs that could work on this scale, and that's part of the benefit of this Euclidean algorithm we're going to get into. This example is not the Euclidean algorithm, by the way. We seek an alternative. Okay, so there's something called the Euclidean algorithm. And what this is a good algorithm for computing GCDs. Okay, so just to get you ready for it, there's one result we just need to be comfortable with to understand why the Euclidean algorithm does what it does, and then we'll explain what the algorithm is. But here's the one preliminary thing. So it relies on the following fact. Let's call this a lemma. Okay, and so we're going to have an equation here relating our two integers, which is exactly the kind of thing that comes up in the division algorithm. So, like, suppose you have, say, A written as BQ plus R, as we do in the division algorithm. I should say, let me say, for example, as we see in the division algorithm. And so the statement of this lemma is going to be about common divisors of A and B and how they relate to common divisors of B and R. And they're in fact the same. So the statement is the set of common divisors of A and B is the same thing as the set of all common divisors of B and the remainder R, whatever that is. Okay, so if we're talking about like two different pairs of integers, like the pair AB and the pair BR, and those pairs have the same set of common divisors. In particular, they would have the same greatest common divisor, and that's really the thing we care about here. So it would follow from what was just said that the GCD of A with B is the same as the GCD of B with R. So we have to just explain this in a minute. We'll prove this and explain it. But the idea is going to be that, when you have such a thing as in the division algorithm, the key thing about the number R, the remainder in the division algorithm, is it's smaller than B. It's smaller than the divisor. So think it's a compared to A and B, it's probably a lot smaller, right? It's a much smaller number. So you might have two really huge numbers here, and you still have one of the huge numbers, but then this one's smaller. So it's the thing on the right is just maybe a little more manageable. Okay, it's got smaller numbers in it. So the idea behind the Euclidean algorithm is going to be to iteratively apply this idea over and over again until the two things you're taking a GCD of are extremely small and you can just manage to figure out what it is. Okay, but before we actually get to the algorithm, we just need to explain this fact. Why do they have the same set of common divisors? And it's actually a pretty short argument in some ways. Okay, and so the proof is this. So suppose, as is assumed, A is BQ plus R. Right, so the point is, in fact, that maybe the right way to process this is this says that A is a linear combination of B and R. And so this says A is a linear combination of B and R. So that's how you can interpret the right-hand side. So what this means then is that any common divisor, of B and R must also divide A. Okay, and so there was a formal proposition we had, which I think was 2.3 or something. But this is something we proved early on. I guess maybe not. Yeah, okay, it was early on. But it said that whenever you have a divisor of two integers, it divides any linear combination of them. Okay, and so we already proved that result. We're just applying it here. So once you have something that divides B and R, it must divide A because of this equation. And you already know it divides B, so now you know it divides both A and B. So if it started it out as a common divisor of B and R, now that it divides A, you know it's a common divisor of A and B. Okay, so any common divisor of B and R is a common divisor of A and B. That's the point. So this shows, it's a little wordy to write out, but any common divisor of the pair BR is a common divisor of the pair AB. So in terms of these two sets over here, the set of common divisors of A and B, the set of common divisors of B and R, we've shown the second one is a subset of the first one. Okay, now you just have to do the reverse and show that any common divisor of A and B is also a common divisor of B and R. It's a very similar argument. Okay, so similarly, okay, all you do is rearrange the equation. Okay, so you rearrange the equation. So similarly, we can write, because this equation is true, we can solve it for R and write it as A minus BQ. So this shows R is R is a linear combination of A and B. Okay, and so what that means then is if you had a common divisor of the pair AB, it would divide the right-hand side, which means it divides R. Okay, so any common divisor of A comma B also divides R. Okay, and so that means, let's leave it here as a note, and so is a common divisor of the pair, which is B comma R. By the way, I'm just trying to talk about pairs of numbers. I just realized the way I'm writing things in this proof is potentially confusing if you've seen other notation. So just something I'll point out to you. If you've ever seen people refer to GCDs with just parentheses and that was it, that's not what I'm doing right here. Okay. And if you don't know what I'm talking about, that's great. Don't worry about it. Okay, but that's the argument. So then they have the same sets of common divisors, so they have the same GCD, and that's it. Okay, so that's the big takeaway. And so then it opens the door to the actual algorithm, the Euclidean algorithm, which we'll use right away. So we'll go back to that same example of two numbers that we factored to find the GCD, but I'll just show you how you would do it to illustrate this algorithm we're about to learn. Okay, so the idea is to do long division, just do some repeated long division. So what we'll do is we'll use this idea. To compute the GCD of 315 and 220, which we do already know, by the way, is 5. We have established that via other means. But here's the idea of the Euclidean algorithm. So the idea is to take this pair of integers and divide the smaller one into the larger one, as in long division. Okay, so if you went to divide 220 into 315, it would go in one time, right? You would have 1 times 220, and you would have a remainder of, I guess, 95. So that's sort of the first step. And we're going to put some steps in between, but the big idea then at the bottom is this. So we'll fill this out as we go. But applying this lemma to this particular equation, it tells us that whatever the GCD of 315 and 220 is, it's the same thing as the GCD of 220 and 95. Okay, so that's supposed to look like an easier thing to figure out, and that's the point. Okay, and then the next point is, you don't just actually figure this out. You say, well, why don't I just do what I did again? Okay, so if you were tasked with finding the GCD of 220 and 95, then you could apply this idea again and say, well, let's take 220 and divide 95 into it. Do long division again. And 95, I guess, goes into 220 twice. That's the quotient, but something's left over. And so this makes 190, so it looks like you have 30 left over. I think. Let's correct me if I'm wrong. Okay, and so then, again, applying the lemma a second time tells you that this GCD is the same as the GCD of 95 with the remainder we got here, which is 30. Right, and that's starting to look like an easier thing to figure out. But still, you don't just figure it out, do the idea again, right? Just keep doing it. Okay, so next you can say, well, what if I took the smaller one, divided it into the other one? So take 30 and divide it into 95, it would go in 3 times, and you'd have a remainder of 5, right? And now, okay, that tells us, keep chaining these together. So that tells us that the GCD we were interested in is the same as the GCD of the divisor we used and the remainder that came out. Okay, now it's starting to get like you really know what that is probably. But let's just do one more step. Pretend we didn't know that the answer was 5, and we said, well, let's do one more division and see what happens. But when you do one more division here, you would divide 5 into 30, and you'd say, oh, well, it goes in 6 times with a remainder of 0. Right? So, fine, you could write one more GCD thing. Right? So this lemma still applies, and it says this is the GCD of 5 with the remainder of 0 that we got. Okay, and the GCD of any positive number with 0 is the positive number, in this case 5. So in this case you would get your answer is 5. Okay, and at some point it actually divided in evenly with a remainder of 0, and that means that the GCD was whatever that was, which came from here. So maybe I'll just put it in a box right here. This was the last non-zero remainder we saw. Okay, that's maybe the way to refer to it. So the last non-zero remainder that shows up in this process is actually the GCD. And anyway, if it helps you visually, when you're looking at this line by line, just note like this divisor becomes the new dividend, and this remainder becomes the new divisor. And that's what's happening line by line. Like the 95 goes over here, 30 goes here, 30 goes here, 5 goes there. Like that. So you could do these repeated divisions. Eventually the process will terminate, and the last non-zero remainder you see is the GCD. Okay, so that is the Euclidean algorithm. I mean, we could formally state it, but that's it. Okay, so I mean, maybe I will just, but I mean, we'll just start it out. Suppose we have, let's suppose we have A and B. These are going to be non-negative integers. Let's suppose B is non-zero. At least one of them needs to be non-zero, but let's say B is non-zero. And you do the following divisions. So let's just try to state it generally. I mean, the first step is divide A by B, and you get a quotient, and you get a remainder. Okay. And so I'm calling the quotient remainder Q1 and R1 because we'll have multiple ones. And let's just point this out, that in the division algorithm, the remainder you get should be less than the divisor, so dB, right? And then next step is you take B divided by this remainder, R1. So you get a new quotient and a new remainder. And the new remainder should be less than the old remainder. And then you continue, right, but next, the R1, which should come up over here, you divide it by the R2, you get a new quotient and a new remainder, and, right, so the new remainder is less than the old one, okay, and so on. And eventually, here's what it looks like at the tail end. Let's write it this way. Eventually you'll have something that looks like this. This is supposed to be the second to last line. minus 1 less than Rn minus 2. And then at the very end, at some point, you go to do division, you get some quotient Q sub n, and you're left with no remainder. Okay, and you just do the process till you hit that point. And then the statement of the Euclidean algorithm is that the GCD of the two numbers you started with is, in this case, what was called R sub n minus 1, which is the last non-zero remainder. Okay, and it always works. It's a foolproof algorithm. It always works. I mean, you can see these numbers do keep shrinking, but this doesn't really emphasize how fast they go to 0, actually. I was going to say, I mean, I just wanted to say something, comment somewhere that this is a really efficient algorithm. Okay, so the amount of work required by this algorithm is something like proportional to how many digits these numbers have, not really the numbers themselves. So it can handle very, very large integers extremely efficient, I guess.
Could we use this to think of high factorization for any integer?
No. No, because you would have to. Because I mean, well, the answer is no, because there's no good way to do that anyone's aware of. But what you could do is you have something you're trying to factor. You could try to compute its GCD with something else, but what's probably going to happen is you'll get 1 is the answer, and then it's no, you got nothing. So you would need to figure out what ought to go here, and that's more or less the same as guessing a factor. So I mean, it's not really. There are cases where you can find factors this way. Like if you just GCD something with something else and you don't get 1, then you have in fact discovered some factors of some integer. But if you work with something like what I said before, my 600-digit number, that's a product of two 300-digit primes. Like you're not just going to be able to find the right beat to get anything. Okay, so anyway. I was trying to tell you factoring is not a computationally feasible thing to do, but computing GCDs is, in fact. You could write you could go home and write a little program in Python or something that takes this idea, and you could find GCDs of 600-digit numbers, and it'll do it in the blink of an eye. It's a very efficient algorithm, okay? If you know how to do that, and you like doing that. Okay, so that is the algorithm. I thought maybe we could do one more example, just to, now that we got it, I hope we have a handle on it, but we can just try another one that we didn't know the answer for. Okay, so, do you have any questions? Yeah, okay. So, let's look at one more example. So we won't do anything too extreme, but here's one that just looking at it, you probably wouldn't know the answer off the top of your head. You know, what's the GCD of that? And so, I mean, you could, if you really wanted to be stubborn, you could try to start factoring things to see what comes out. But let's just use our algorithm. Okay, so it's not so bad. We would divide the smaller number into the larger number, which the quotient would only be 1, right? And then what's the remainder is the difference of the two numbers, which I guess is 504. So okay, and then next line is we would want to take 735, right, and divide 504 into it, which would again only go in one time. With a remainder of whatever the difference of those two numbers is, which is 231, I believe. Okay, and so then we do some more division. Take 504, we'd like to divide 231 into it, which should go in twice this time. That'll give us 400 something. So Right, so twice that is 462, and I believe what's left over is 42. Okay, and so anyway, what you notice though is their numbers are kind of shrinking. At this point, we're dealing with this smaller number and this 2-digit number. So you could divide 42 into 231. That should go in 5 times, I think. 5 times 40 is 200, so that makes sense. What's that? That's 210. So that's 210, which means we have 21 left over. Okay, and then next step would be to take 42 and divide 21 into it. Okay, that's a good one. So 21 goes into 42 evenly, goes in twice, and that's it. Nothing left, right? So there we go. That is right here then. Right? Our last non-zero remainder, that is what we recognize as the GCD. Okay, so GCD over our two numbers. 1239 and 735 turns out to be 21. Okay. So that's the idea. Make sense? You good? So we'll have to use this a number of times. It's all like, it's something tedious about it, but it's not sophisticated or anything, right? It's just division, right? Just division. Okay, so there is a byproduct of this that we are going to need in several places. So this is 2.7.1. Sort of a continuation of this. So this was called the Euclidean algorithm. It's an algorithm for finding GCDs. Now, there's something you can build off this called the extended Euclidean algorithm. And this is turned out to be really useful for a lot of things we're going to do. So you might say it's surprisingly useful. So the following surprisingly useful result is a consequence of the Euclidean algorithm. So we'll see what it has to do with the Euclidean algorithm probably next time. But I want to state this and maybe think a little bit about an example or two. So this is theorem 212, which is going to be a pretty important theorem for a lot of what we do early on in this course, maybe even later. But the statement is that there exist integers so there exist integers x and y such that the GCD of A and B can be written as AX plus BY. Okay. So anyway, this starting with a pair of integers A and B, that's probably, I should have been a little more precise in stating it, but the statement is like given a pair of A and B. So given a pair of integers A and B, given a pair A and B, you can find integers x and y such that AX plus BY is equal to the GCD of A and B. So, for example, what this is asserting there are integers x and y, with the property that, like maybe just look at this example. The GCD we got here was 21. So 21 can be written as 1239 times x plus 735 times y. Like that. That's what it's asserting. It's possible to find numbers to make that true. Okay, so this is, this is a linear combination of the two integers in question. It's a multiple of one number, and a multiple of the other number added together, and somehow you get exactly 21. So, given the sizes of these numbers, it's probably evident that one of x or y is negative and the other one's positive, right? So it's, one of them is something big you're adding, the other one maybe is something big you're subtracting, and it cancels out pretty well to just leave 21 somehow. Okay, so what is supposed to be the case, since this is a true theorem, it can't be done, but it's not probably particularly clear what x and y should be, right? How can you add a multiple, how can you take a multiple of 1239 and maybe subtract a multiple of 735 in order to get exactly 21? Not so clear what the right multiples are. Okay, so that's true, it's not clear. It takes some work to find them. And so that is what this extended algorithm is going to be for us. So the extended Euclidean algorithm this is an algorithm for finding x and y. And so we will have a number of uses for these two things. I just want to tell you, we'll learn how to do this next time, but just to maybe reinforce the point that it probably wasn't too clear where these come from. In this particular example, just if you wanted to know, and we'll work this out next time, is that you actually have to subtract 16 1239s from 27 735s. I guess I wrote it asymmetrically, is the way I wrote it above. But the x is minus 16, the y is 27. Maybe you never would have thought that. It's often the case, so we're going to have a nice foolproof algorithm for finding these things. So look at it next time. Yeah?
Are these x and y unique?
They are not unique, by the way, just so you know. They are not unique. There would be ways to change, well, okay, but that's one way to do it, I guess. Okay, so we don't have time to get into it now, so we'll call it a day, and next time we meet, we'll get into this process.